In this module, we touch upon the basic properties of particle acceleration and detection methods. In this video and in the next, we will discuss charged particle detection techniques. First, we talk about ionization detectors in general and gaseous ones in particular. After watching this video, you will know how gaseous ionization detectors count charged particles and measure their trajectories, and which operational modes such a detector can have. Ionization detectors detect the passage of a charged particle by measuring the total charge of electrons and/or ions produced by the ionization of the medium. This medium can be a gas, a liquid, or a solid. To collect the electrons and the ions before they recombine into atoms, an electric field must be present which separates the charges and makes them drift towards electrodes. The charges induce a small current on the electrodes, a signal which can be detected through an amplifier. The average number of electron pairs, electron-ion pairs, produced during the passage of a charged particle is given by the Bethe-Bloch formula that we have presented earlier, with D being the thickness of the detector and W the average energy required to ionize one of its atoms. In a gas, W is typically of the order of 30 electron volts. The size of the detected electrical signal depends on several technical factors, but mostly on the applied high voltage. So this graph shows the most important operational regions. On the y-axis you see the detected charge in a logarithmic scale, and on the x-axis you see the applied high voltage. The first useful region for particle detection is the ionization region, where the voltage is large enough to prevent ion-electron recombination, and the ionization charges drift towards the electrodes. The resulting signal reflects then the total ionization charge. The advantage of this operational region is that you obtain an excellent energy resolution and a very good linearity. The obvious disadvantage is that the detected signal is very small, since there is no internal amplification in the detector itself. So special low noise amplifiers have to be used in order to render this signal detectable. This operational mode is used in ionization chambers filled with gases or noble liquids. Also, solid-state detectors made of silicon or germanium, which will be discussed in the next video, work in this region. The next useful region for particle detection is the proportional region. If the field is high enough, of the order of 10 to the 4 electron volts per centimeter, electrons are accelerated by the electric field and gain enough energy to produce secondary ionization. The total number of atoms ionized grows exponentially with the applied voltage, as shown in this graph. The amplification factor is between 10 to the 4 and 10 to the 8, and the large amplification factor can especially be obtained in gases, which is why detectors operating in this region are mostly gas-filled. The advantage of using this region is that there is no need to have a very low noise electronics, since there is internal amplification in the detector itself. The disadvantage is that the energy resolution is worse because of fluctuations in the amplification process. These fluctuations are mainly used to instabilities in external parameters like the high voltage, the temperature, the pressure, etc. Detectors operating in the proportional region are mainly used to measure the position of particles. Drift chambers, proportional wire chambers, and so on use this operational region. In these chambers, the electric field is implemented using thin wires to put as little material as possible in the path of the particle. As an example, we show here the central drift chamber of the L3 detector at the Large Electron Positron Collider at CERN. As the particles lose very little energy in the gas by dEdx, the measurement is not destructive. Wire chambers are ideal to measure charged particle tracks in front of a calorimeter, which will then measure the particle energy by absorption. We will talk about spectrometers and calorimeters in video 3.10. The last useful region of a gaseous ionization detectors is the Geiger region. If the field is increased even more, the energies of secondary electrons increase rapidly. and they excite or ionize other atoms. Thus, an avalanche of free electrons is produced. Furthermore, a large number of photons is produced when the atoms fall back into their ground state. These photons add to the ionization by photoelectric effect along the wire where the electric field is strongest. The avalanche develops quickly and an audible discharge is produced. This is the principle of the Geiger counter. Due to the discharge, the current on the anode is saturated. The signal amplitude is thus independent of the primary charge. The advantage of using this region is that low radiation levels can be measured by counting particle rate, even if the particles have low energy. The disadvantage is the energy of the particles cannot be measured. The discharge stops when the space charge formed by the positive ions around the anode decreases sufficiently the electric field so that the avalanche process stops. The detector will be insensitive to new ionization until the positive ions have migrated far enough from the anode. This is the origin of dead time in a Geiger counter. A further increase in the electric field produces a permanent discharge. A short circuit between cathode and anode, which will eventually destroy the device. Here's a picture of a Geiger counter which makes an audible sound every time a particle is counted. And in fact, I've brought a Geiger counter here. It has the Geiger tube fixed to the electronics and the counting device in this base. So if I switch it on, you can hear the audible sound created by the device, which is where the counting rate is mostly due to the gallium radioactive isotopes inside my own body. In the next video, Mercedes will discuss semiconductor-based ionization detectors.